Thank you very much for that lovely introduction. And good morning, ladies and gentlemen. I'm going to take a liberty and just address the arachnophobes in the audience. So I don't know how you deal with spiders, whether it's just shutting your eyes, grabbing a brown paper bag, or leaving the auditorium. But I'm just giving you several seconds to understand that there are spiders in this presentation. I'm serious, there are spiders in this presentation. So the spider swung its abdominal spinnerets upwards, pinching the web between one foreleg, then another, building the growing spiral out of a set of slightly asymmetric rectangles. Wire-cutter feet pinched the silk in an automated process, appearing somewhat over-engineered for the purpose, with too many legs and the choice of 7 kinds of thread. Yet the omnivigilant eyes ensured there were no mistakes, and in those moments, the spinning machine existed only to turn and weave a ball of silken thread forever. So I'm curious, is spider silk making a natural activity, like thinking or running? Or is it a creature's technology which helps it make a better way in the world? I mean, not all spiders produce spider silk. So I just want a show of hands. Who here thinks that spider silk is an entirely natural phenomenon? Can you raise your hands? I'm just going to try and squint into the darkness. So that's just over half of you, actually. And who thinks that the spider is a supreme master of technology? Oh, that's very few, actually. So I'd say about 1/3 of you think that the spider is a supreme master of technology, and about 2/3 think that the spider's web spinning is entirely natural. So whilst at first this may seem an obvious question, what is nature? What is technology? The distinctions are actually very, very far from clear. And notably, of course, Dutch designer Kurt van Menswoord explores this entanglement of culture, technology, and ecology in his concept of next nature and considers the design implications. Now, according to modern conventions, it's pretty clear exactly what is a technology, because we equate technology with machines that are made of metals and plastics, manufactured objects, and they're powered by cables that pipe electromagnetic waves as oceans into our homes. But in an age of biotechnology, where the agents of useful work are in themselves a function of life, the boundary between creature and technical system has become indistinct. In her book, The Universe of Things, Gwyneth Jones imagines an alien civilization whose biology is extended into its surroundings as a wet, technological, chemical network. Yet it would be a mistake to think that Jones is simply talking about an alien species. These are very real characteristics of our very own bacteria. And sociologist Myra Hurd takes a bacterial perspective of the world in her book On the Origins of Sociable Life, and observes, like her mentor Lynn Margulis, that the bacterial realm is highly creative and resourceful. Microbes can perform all kinds of operations and even use extrusions of their own bodies to manipulate their environment. In other words, bacteria continually make their own technology and even exchange it with each other by communicating using a physical and chemical language that enables them to coordinate actions in complex ways called quorum sensing. And this enables them to behave like a multicellular organism. So bacteria use their technology in very much the same way as humans do, to reap the benefits that would otherwise be unattainable to them as natural individuals. So with the advent of biotechnology and the new science of synthetic biology, it is now possible for us to work alongside the inherent creativity of the natural world, which we so often take for granted. And we produce even more extraordinary things using this common language of physics and chemistry, and particularly in synthetic biology. We're using a very unique kind of chemistry called DNA. Now, when I talk about chemistry, I don't imagine it in an abstract manner, like the sets of equations that I learned at school, and you probably did too. I think of it as the spatial relationships between everyday substances that take place at the molecular scale when they approach each other, a bit like the crystal formation on this picture, which are formed by crystals called biomorphs, which take on rather flower-like patterns under certain conditions. So like bacteria, all substances have the power to communicate, whether they're technically alive or not. Quantum theory has revealed that when one set of atoms approaches another at the nanoscale, they may influence each other in different ways. In fact, matter can communicate through tiny charges, as well as strong and weak subatomic forces. And these create new molecular spaces and forge compound structural systems. So under steady state conditions at the lowest possible energy levels, not much happens as an interaction between different substances. But at far from equilibrium, when the molecules themselves possess a certain amount of energy, then new kinds of operations become obvious at the human scale. So what if? What if we could understand the powerful molecular language of physics and chemistry, just like bacteria do? What kind of technology might we make? And what kind of a world might we have access to? And if you've got trouble in imagining in terms of bacteria and chemistry, I'd just like you to think of what tiny spiders might do. So in order to demonstrate this possibility, I used a chemical system that's been around for a long time. It was first described in 1892 by a zoologist called Otto Büchli, who was trying to show that biology was just a kind of chemistry, just more complex. And what he did was he added a highly alkaline droplet, which in this particular film is stained blue, so you can see it clearly, into an oil field. And it looks like a detergent advert at the moment. The droplet is spreading out, and it's breaking up, and you can see tiny bodies in the middle of that field. And if you can just squint a little bit into that field, because it's just visible with the naked eye, each of those droplets are a millimetre or so in diameter, so they're much, much bigger than bacteria. You can see that they've got a movement of their own. And Büchli thought that he was seeing what he called a protist, a simple-celled organism. In other words, he thought this was like a chemical form of life. So what's interesting about this system was that it was the first, it's only like a soap-making system, developed about 100 years ago. And it hadn't been looked at using modern technology until I went into the lab in 2009 and used a modern microscope. And what was very interesting when I looked at this in detail was just how lifelike these central droplets were. They were able to move around their environment, they could sense it, they could respond to the presence of other droplet bodies, and they could even make microstructures. And they behaved a way that was quite sociable. I'm anthropomorphizing wildly here, like Myra Hurd. But they started to form little groupings, which Deleuze and Guattari describe as assemblages. And so it's probably the wrong way of saying the French, but I'm going to call it natural computing for obvious reasons very soon. So these groupings of matter that are very lifelike can be imagined as technological operating systems. And they have a very unique set of properties. And as you can see, they're extremely lively. And you might think that that would make them absolutely impossible to work with, like trying to pin a jelly to the wall. But actually, they're rather conservative and predictable in their behaviors. And you actually see them existing between limits. And the more that you live with these little creatures, I'm going to call them creatures, I know they're not technically alive, they don't possess any DNA, they don't have any central organizing program, but you start to get to see inside their world, a bit like Myra Hurd crawling into the realm of bacteria. So here is my favorite movie of all time, because this is an interaction that they show where they start to create a surprising change in their behavior and in the way that they move. And this is something that other technical systems like cybernetics and machines do not show. They don't undergo these radical transformations. So here you can see the little droplets that were quite happily making microstructures, which are probably a couple of centimeters long in that case. And they suddenly undergo this radical transformation. And this is a unique characteristic of this particular technical platform. In other words, there are certain sets of properties associated with the assemblage, or the natural computer, that really we can exploit to give us kinds of operations that do not exist with other forms of technology. And this becomes very useful in terms of design. So now we have a set of bodies that can cooperate in a coordinated way. We don't entirely understand all the details of the system, but maybe we can look at this technical platform in a slightly different way to, say, classical science, which likes to analyze all the parts and look downwards for answers. And maybe we can start with this technical platform and look sideways and upwards to see what this existing set of conditions can do. So it's really important that we're able to speak the language of physics and chemistry, because this is what underpins the coordinating actions of these bodies. And this can be done using a set of emerging fields of science called natural computing. And so I'm going to call these natural computers from now on, so that I don't have to use the term assemblage. So I decided to see just how natural computing could be used to create design opportunities in the built environment. So immediately I'm just challenging these things that exist at the millimeter scale to deal with much bigger architectural realms of operation. And I consider these not to be deterministic technologies. I can't program to do exactly what I want them to do. And they are probabilistic technologies. So this is a form of probabilistic design. It's not speculative design, because at this stage, it's not imagining what it's going to be. It's working with a set of possible operations and seeing and directing how those actually unfold. But the Future Venice project is a speculative project that engages with probabilistic design and also speculative design. And so it proposes an alternative to the current solution to the increasing floods that are very damaging to the city of Venice by creating a big barrier between the Adriatic Sea and the fabric of the city itself. It's constructed 78 hydraulic gates called the Moses Gates, which operate like a giant robotic King Canute to literally hold back the tide. So how might a natural computer address this challenge differently? So we imagined an artificial reef growing underneath the city, and the city's in a unique position in terms of its foundations. It stands on wood piles. Let's think of them like stilettos. It's standing in the mud. So it means that we can actually design a set of droplets, a bit like the ones that we've just seen on the screen, to move away from the light, so we can give them a metabolism, a particular kind of set of chemistries. And this metabolism is activated by the light, so it drives them to a much lower energy state, which is down under the darkened foundations of the city. Now, when the droplet's at rest, a second metabolism kicks in, and it becomes the site for the accretion of minerals that are dissolved in the lagoon, and also dissolved carbon dioxide. So it starts to build tiny little shell-like structures. And gradually, these are fixed into an artificial limestone-like reef underneath the city's foundation. In other words, we've just put Venice on a set of platform boots. And so the platform boots are spreading the weight of the city over a much broader base. And when we did field studies on this, because there's a problem with actually doing the experiment in Venice live. We've taken out big fish tanks, which are hideous to carry around the narrow, crowded streets of Venice. But it's a UNESCO World Heritage Site, so you can't just go leaping into the lagoon and putting little lifelike chemistries there. You get into a lot of trouble. So what we did was we did the field studies, and we actually noticed that there's a lot of bioconcrete, a lot lot of accretion material that's being produced by the natural marine organisms that actually live in Venice. So we started to imagine a different role now for this technology, not as one that has this totalizing program like a machine, but one that could actually work alongside the biology that is living in the city itself. So it becomes a kind of language between the desires of the city dwellers and also the natural ecologies. It also has a very interesting property, this idea of a natural computer, in that if the environmental conditions change, so can the performance of the droplets. So, for example, if Venice dries out instead of drowns, which is the current predictions, then as the waters subside, they leave a little trace of bioconcrete behind them, and they seal off the wood piles from the air. And of course, it's when wood piles get exposed to the air that they start to rot. So in some ways, this is actually producing a material that could be very useful for the future of Venice, particularly if, like Pietro Tirtini et al., they're thinking of anthropogenically lifting the city by reinflating the aquifers that have been drained by industry. So from a speculative project, one that works with a probabilistic technology, we can start to see how a real solution for some of Venice's challenges, not all of them, but some of them may emerge. So Venice was a very interesting site because it's an ideal location for exploring the potential of natural computers as an architectural technology, because the watery foundations create the conditions in which matter can move and flow around the site. Now, the importance of infrastructure cannot be overstated in supporting the activity of natural computers, as living processes, just like us, need resources to support their actions. But by designing airflow as breathing systems rather than vents, and water supplies as circulations rather than drains, then it is possible that our homes and cities could become life-promoting sites, not just for humans, but for entire ecologies. And so with the appropriate flow of resources through urban infrastructures, it may be possible to use a whole range of biological and chemical technologies that could perform the kind of work that we would normally expect of machines. For example, bioprocess-enabled organs could perform a range of metabolic functions, such as fixing carbon, producing heat, filtering water, or even making fertile soils. And such systems could be invisible to the inhabitants within homes by occupying under-imagined sites within our domestic spaces, like under floorboards or in cavity walls, which are just full of toxic chemicals right now. But they could also be highly visible and fetishized objects, as in Phillips's microbial home, where bioprocesses like green microalgae or colonies of hard-working bacteria transform waste products into useful substances that are then exchanged and transformed within the building through a locally defined ecology. So strategically positioned, these architectural organs may give rise to buildings with physiologies that act as life-promoting oases for human and non-human communities. And in case you think that this is a world of science fiction and it doesn't exist yet, such developments are actually taking place. This is a photograph, not a rendering, of a building built by Arup this year, which have created the world's first algae facade. Now, this houses little green cows, or algae, that munch on carbon dioxide and sunlight in a closed ecosystem within a building to produce biomass, which is dried and burned to create energy for the building, which is fed back into the system. So already we're starting to see some of these designed ecologies taking root in architectural design practice. Now, what design could do to help technological diversity, because I'm not against machines, it's just that it always ends up as being the only metaphor and the only option that we have when we think about an architectural system or if we're trying to make products in design. So I think that design can help us explore how the convergence of technology through a program called Nano-Bio-Info-Cogno technologies, which were a set of emerging technologies that were identified by broke out in Bainbridge for the National Science Foundation in the United States and has since been taken up by Europe, how these emerging technological platforms could potentially create new sites of transformation within our cities, not necessarily as a totalizing paradigm, so the whole of Amsterdam looks like a rainforest, but rather, there may be little sites of bioaction and biodiversity within our cities, transforming them from being deserts of concrete and tar macadam into sites of biotic regeneration. And I think the other point of design in these particular contexts is to really set new visionary agendas. It's really difficult to think of something other than modernism, a more sophisticated, shinier, more powerful, ecologically friendly looking machine. So I think that what design can do is really help us escape what I call the technological trap of modernism and help us enter into strange new quantum biological spaces. And so the robot spider spun until the frazzled wasp landed in its web. Then a different program kicked in. The legs once nipping as delicately as a lace maker now held the six-legged prey in its surgical grip. The filament-fine silk splayed into a suffocating elastic film. And so began the visceral draining of life, in which the majesty and brutality of the animate world differed so radically from any machine, and displayed itself in full view on a shimmering web in glorious technicolor. Thank you. Yeah, questions.
Are you okay, Rachel?
I'm okay with questions. I apologize to the arachnophobes as well.
I mean, really stimulating, and I'm sure for those who work in the built environment as well, opens up a huge amount of opportunity. And I wondered, how is your conversation going with architects, because is this going to unleash a sort of a new aesthetic, new materials? Often when concrete came along, then we ended up with a whole new movement in architecture. So will this, do you think, is there an aesthetic that will go with this?
I think if you look at the photographs I've taken, I've resisted, I guess, defining an aesthetic, because I see it very much as being an open, emerging network of possibilities. And I think that the conversations I'm having with architects and construction engineers and even building developers is one that is creating new opportunities. So I think the vision is still emerging. I think that there is something, again, quite probabilistic about the outcomes. If anything, it's serving a conversation that needs to happen about how we reach escape velocity from modern aesthetics.
And how, sort of, in a way, how near to the market do you feel what you are, because you're really in the discovery field here.
Yes.
But how near to really bringing some of these to life in buildings?
I would say that Arup's taken the first leap.
Yeah.
They've invested an awful lot of money in making those algae facades work. We would like to work with them to develop the systems, the value chains that talk about new kinds of green citizenship. Beyond the simple economics, or the kind of, the economics of resource scarcity, we would like to, develop new ways of thinking about the value of these kinds of buildings. But in terms of the actual technologies, they're all there. It's really just about gardening and bringing together the threads that already exist. It is not beyond our capabilities to create circulations using 3D printers, even if we do it in very small sites within a building. We don't have to transform the entire built environment at once, and I don't think we should. I think that this is very much an ongoing experiment, and I think that there is plenty of room for many kinds of design and many opportunities for technological innovation.
And I know you're working on this living starship.
Yes.
Is that a provocation, or do you feel that that's... I mean, was that there to stimulate the debate, or actually... Does that have a sense of reality about it?
I think it's both. I think that many of these speculative projects, I think Daisy was talking about it yesterday, that many of these speculative projects actually do have real-world implications, but you have to open up that space first. So the idea of the design and construction of the living interior of a world ship is part of a real project that was proposed by aerospace engineers, that they wanted to build a starship in Earth's orbit in the next 100 years. And that's actually an industry consensus. I think the consensus is actually to do with the next wave of space exploration, which is going to go beyond interplanetary space and into this, into interstellar space. And if we're going to do that space, interstellar space is an incredibly long way away. Douglas Adams was not joking about that. Yeah. So essentially, we need to start that kind of thinking now. And I think the other part is, how do we think across generations? How do we inspire young designers and engineers now, and without shutting down the options for further developing platforms? And I think sometimes if you create a rigid aesthetic, it actually just creates another ism rather than, I guess, a whole new way of thinking about space and design.
You've got everybody here thinking about this now as well. Rachel, thank you very much for stimulating us.
Thank you.